Section: Introduction. In this section, we discuss the challenges faced by large language models, LLMs, which perform well on various tasks but depend on vast amounts of internet data. This data can contain problematic elements, like copyrighted content and personal information, leading to unintentional memorization and generation of such data. Moreover, LLMs are limited by the time frame of their training data, making them unaware of events or updates that occur afterward, which can result in outdated or incorrect information. Retraining these models to fix these issues is costly. For instance, pre-training Llama 3 requires millions of GPU hours and generates significant carbon emissions. To keep LLMs relevant and useful, we need to create methods that allow them to 1. Forget problematic or outdated information, 2. Learn new information, and 3. Maintain their performance on standard tests. Without these abilities, LLMs can pose serious legal and ethical risks, as evidenced by lawsuits from content creators like the New York Times against companies that use copyrighted material for training. As LLMs become more common, the risk of spreading outdated or legally sensitive content increases, which can have serious consequences. To tackle these issues, we propose a framework called LLM Surgery, aimed at efficiently updating the knowledge of LLMs to keep them current, accurate, and legally compliant. Our main contributions include 1. Creating an objective function that helps the model unlearn data, learn new data, and minimize differences in outputs between the old and updated models, all without needing expensive annotations. 2. Developing a comprehensive dataset that includes sets for unlearning, updating, and retaining information for both training and evaluation. And 3. Providing empirical results that show significant unlearning, improved accuracy on updated data, and stable performance on retained data. In our proposed methodology, we work with 3 datasets: the unlearn dataset, the update dataset, and the retain dataset. Our goal is to adjust a pre-existing LLM so that the new model meets 3 criteria. 1. It forgets specific information from the unlearn dataset. 2. It incorporates new knowledge from the update dataset. And 3. It maintains performance on standard tasks using the retain dataset. The LLM Surgery framework optimizes an objective function designed to achieve these 3 goals. The first part encourages the model to forget specific information by adjusting parameters in the opposite direction of learned patterns from the unlearn dataset. The second part helps the model learn new information from the update dataset. The third part ensures that the model retains important knowledge by minimizing differences in output between the updated and original models on the retained dataset. In summary, we aim to create a more efficient and effective way to update LLMs, ensuring they remain useful and compliant with legal standards. Section Summary. In this section, we highlight the challenges faced by large language models, LLMs, due to their reliance on extensive internet data, which can include problematic content and outdated information. We propose the LLM Surgery framework to efficiently update LLMs by enabling them to unlearn specific data, incorporate new knowledge, and maintain performance on standard benchmarks, thereby addressing legal and ethical risks associated with their deployment. Section: Experimental Setup. In this section, we describe our experimental setup using the Llama 2-7B model to test the LLM Surgery framework. Our goal is to unlearn information from a specific dataset, update the model with new knowledge, and maintain performance on another dataset. First, we continually pre-train the Llama 2-7B model on both the unlearning dataset and the retained dataset. This step ensures that the model has knowledge from these datasets before we apply LLM Surgery, and we refer to this pre-trained model as theta pre. For our baseline model, we could simply pre-train the Llama 2-7B model using only the update dataset and the full retained dataset. We call this model theta baseline. However, this method is costly and time-consuming, especially since the retained dataset is much larger than the update dataset. Our challenge is to make the necessary changes efficiently while keeping the model's overall performance intact. To address these challenges, LLM Surgery utilizes the general knowledge from the retained dataset already present in theta pre to make specific adjustments, resulting in the modified model theta surgery. Instead of starting from the off-the-shelf Llama 2 to 7B model, as we do with Theta Baseline, LLM Surgery begins with Theta Pre. This method effectively unlearns specific information using the unlearning dataset, incorporates new knowledge from the update dataset, and maintains performance on important tasks using a small portion of the retained dataset. Importantly, it avoids the high costs associated with retraining the model from scratch. Since there are no publicly available datasets tailored for our task, we created a new dataset and evaluation benchmark. This benchmark includes multiple-choice question-answer examples generated with GPT-4, featuring questions, 3 answer choices, and labels for the correct answer. We use accuracy as our evaluation metric. For the unlearning dataset, we derived it from the original Wikipedia biographies in the WikiBio GPT-3 hallucination dataset, which contains 238 true biographies. We split this dataset into 2 parts, one with 119 biographies used to simulate problematic data, like personal or copyrighted information, and another with 119 biographies representing outdated information. To evaluate the effectiveness of LLM surgery in unlearning this content, we generated 2,400 multiple-choice question-answer examples based on the unlearning dataset. The update dataset consists of 119 fictitious biographies created in a Wikipedia style using GPT-4, corresponding to the same subjects in the outdated subset of the unlearning dataset. This ensures that Theta Pre has not encountered this content before LLM surgery. We also generated 2,400 multiple-choice question-answer examples from the update dataset to assess how well Theta surgery incorporates this new information. To ensure that our model modifications do not harm performance on unrelated tasks, we created a retained dataset with 2 million tokens from the Open Web Text dataset and 1 billion tokens from the Red Pajama V1 dataset. While both Theta Pre and Theta Baseline use the entire retained dataset, Theta Surgery only utilizes a small subset to maintain the model's original performance. We developed an evaluation benchmark with 20,000 multiple-choice question-answer examples from the Open Web Text dataset to confirm that Theta Surgery's performance remains consistent with Theta Pre. Additionally, we evaluate Theta Surgery on the ArcEasy benchmark to ensure it retains performance comparable to the off-the-shelf Llama 2 to 7B model. Section Summary. In this section, we describe our experimental setup using the Llama 2 to 7B model to assess the LLM surgery framework's ability to unlearn information, integrate new knowledge, and maintain performance. We continually pre-train the model on specific datasets and utilize a novel evaluation benchmark to ensure efficient modifications without the high computational costs associated with traditional retraining methods. Section: Results. In this section, we demonstrate the effectiveness of the LLM surgery framework by examining the accuracy of the continually pre-trained Llama 2 to 7B model across various evaluation benchmarks: unlearn, update, and retain. We compare the model's performance before and after applying LLM surgery. Our findings show that after surgery, the model's accuracy on the unlearn benchmark decreased by 19% compared to its pre-surgery state. Additionally, it performed 4% worse than the standard Llama 2 to 7B model, confirming that it successfully unlearned the targeted information. On the update benchmark, however, we observed a 20% improvement in accuracy, indicating that LLM surgery effectively incorporates new knowledge. Importantly, the model maintained similar performance on the retain and ArcEasy benchmarks, suggesting that LLM surgery does not harm its understanding of unrelated tasks. To evaluate the efficiency of LLM surgery, we compared its runtime to the naive approach used to create the baseline model. We found that the surgery model achieved the same performance level as the baseline but required 35 times fewer GPU hours. This efficiency stems from the smaller size of the unlearn and update datasets compared to the retain dataset. Unlike the naive method, which retrains using the entire retain dataset, LLM surgery only uses 2% of it, aided by the KL divergence term in our objective function. These efficiency gains become more significant as the retained dataset grows, showcasing the scalability of LLM surgery. Next, we conducted ablation studies to assess the contribution of each term in the LLM surgery objective function. In the first study, we used only the gradient descent term, which improved accuracy on the update benchmark but resulted in a 10% higher accuracy on the unlearn benchmark, indicating inadequate unlearning. Additionally, accuracy on the retained set dropped by 8%, suggesting that relying solely on gradient descent can lead to forgetting previously learned tasks. In the second study, we included both the gradient descent and KL divergence terms while omitting the gradient ascent term. This approach preserved performance on the retained dataset but failed to unlearn the targeted information, as there was no accuracy drop on the unlearn benchmark. The KL divergence term likely hindered effective unlearning, showing that the gradient ascent term is crucial for this process. It allows the model to achieve a 19% reduction in accuracy on the unlearn benchmark, confirming that all three terms are necessary for efficiently and effectively modifying LLM behavior. Section Summary. In this section, we demonstrate that the LLM surgery framework effectively reduces targeted knowledge by 19% while improving accuracy on new information by 20%, all while maintaining performance on unrelated tasks. Additionally, we show that LLM surgery is significantly more efficient, achieving the same performance as a naive approach with a 35x reduction in GPU hours, highlighting the importance of all components in the objective function for effective unlearning and updating. Section: Activation Pattern Analysis. In this section, we analyze the activation patterns of our models across three datasets: the unlabeled dataset, the updated dataset, and the return dataset. We observe that these patterns are consistent for both the standard Llama 2-7B model and our pre-trained model. This consistency likely arises because Llama 2-7B was initially trained on Wikipedia biographies and other sources, which reinforces similar knowledge in our pre-trained model before we apply LLM surgery. After we perform LLM surgery, we notice that our modified model exhibits different activation patterns for the unlabeled and updated datasets. This change occurs because LLM surgery allows the model to forget the information from the unlabeled dataset while integrating the updated dataset, all while maintaining its performance on the return dataset. Consequently, the activation patterns for the return dataset remain similar between the pre-trained and the modified models. We also discuss related works in the field of unlearning in large language models, LLMs. Some methods aim to eliminate harmful content but require expensive fine-tuning and additional annotated datasets, which limits their scalability. Other approaches focus on editing structured knowledge but are usually effective for only a few concepts and do not adequately address the unlearning of outdated information, leaving models exposed to potential information extraction attacks. In contrast, our method combines unlearning and editing, allowing us to remove problematic data while updating the model. We avoid the need for costly annotations by using a continual pre-training objective, making our approach scalable for unstructured data and large token sets. Additionally, our work meets regulatory requirements, such as the Right to be Forgotten Act, which necessitates direct changes to LLM weights, something that in-context learning and fine-tuning cannot achieve effectively. We also note that existing datasets do not fully evaluate unlearning methods. For instance, some efforts to reduce hallucinations by editing Wikipedia biographies may be biased due to pre-trained knowledge. To overcome this, we introduce a new dataset where the update data is not seen by the model before editing, allowing for more accurate evaluations and supporting our unified approach to unlearning and model updates.